Thanks for having me here. I'm going to talk today about a tool I built called the Go Guru. I work on the Go team at Hooli in New York, and one of my first tasks when I joined the team was to add some features to Google's implementation of its Go implementation of its RPC system. And this is a complex piece of code. It's a large piece of code. It has a lot of features for resilience, for security. It's highly optimized, a lot of concurrency. And it was a difficult thing to change just because I didn't know my way around it. And as I was working on that change, I realized that there were tools that we could build that would make that easier. And so that's the origin of this tool I'm going to talk about. So I describe it as an editor-integrated tool for navigation and code comprehension. So unlike traditional IDEs, which require that you use their editor and their graphical interface, this one tries to meet you where you are with your existing editor, whether it be Emacs or Vim or any other editor. And it tries to answer the kind of questions that come up all day long in any typical day of programming. You can think of it a little bit like a headless IDE. It provides the analysis, but your editor provides the user interface. Originally, this tool was known as the Oracle, and I like this name because it reminded me of the ancient Greeks who would come with their questions to these mysterious princesses at Delphi, and they would get back answers that were true but often very mysterious about their questions. And that, for me, captured a little bit of the spirit of this tool. Unfortunately, someone pointed out that the name Oracle was already in use for something else, and so I renamed it Guru, which captures still a little of that mystique. So the talk will be in 4 parts. The first 3 will discuss different groups of features of the tool. The first is about features related to names. The second about features related to types. And the third about aliases, that is, the relationship between references and the things that they refer to. And then finally, I'll finish up with a discussion of some challenges and future work. And along the way, I'll just point out how some of the details of the implementation, how the editor actually interacts with the tool. So what's in a name? There are 2 purposes to a name in a program. The first, the one that we think about most often and the one that we discuss the most, is as documentation. A good name means we don't have to add a comment explaining the purpose. And there are lots of conventions that we all understand that help us to communicate meaning through names. But a compiler doesn't care about a name, and often programmers don't either. We use names like X when we have nothing to say about a value. To a compiler, a name is actually an indication of a structure, a graph, a relationship between references and declarations. And it's this structure here that is one of the most fundamental organizing principles of programs that the tool can help you to visualize and navigate. So the 2 questions that we often have about names are, where is this name defined, and who else in the program refers to this name? And so I'm going to show you some of the features of the tool that can help you see this. In parentheses here, I've shown you the name of the Guru command. The what command does identifier highlighting. The definition command jumps you to the definition of a declaration, of a name, and the referers command shows you all references throughout the workspace. So I'm going to switch now to some code. I hope you can read this at the back. So first of all, I'm going to show you highlighting. We're in a program here which is a little chat server in 80 lines of Go code. Some of you may have seen it in my book. If you hover over an identifier, such as con, you'll notice that the editor is actually showing up all the occurrences of identifiers that refer to the same thing. And it happens very quickly. And so it helps you to see immediately the structure, the graph that's implicit in this use of names in your program. And in fact, on some occasions, it actually points out bugs. I've noticed that it's very easy, because of the somewhat subtle short-form declaration, the colon equals statement in Go, to not quite know where a variable is being declared. You'll see in this program, when I hover over the error variable, it highlights 3 uses. But down here, there's another variable, also called error, that's actually completely distinct. And especially for novice programmers, this feature of declarations in Go can be a little subtle. But here it's visualized directly for you. The next thing I want to show you is jumping to definitions. So this is a feature that, if you've used an IDE, you'll be very familiar with. Let's pick a name such as messages. I'm going to do a Guru jump to definition query here. It takes me to it. This one's easy because it's in the same file. Let's try a harder case. Buff.io.newScanner is obviously defined in another package. I do a jump to definitions query, and it takes me to the location where it's declared. Let's do a final one. So input.text is a method. And again, jump to definition takes me to the declaration. The next feature is referrers. So if you hover over an identifier and ask for a referrers query, this time the tool outputs its result into a new editor buffer. And you'll notice the format of this editor buffer is very similar to what you get when you run a compiler from inside your editor. It's a set of locations in the source code and a piece of text. So this way I can step through all the references. This one, again, was easy, and the green highlighting pretty much told me the answer already. Let's try a more complex one. So net.listen is an exported identifier defined in another package. So when I do a referrers query this time, it actually has to inspect potentially a whole lot of packages throughout your workspace, and it finds hundreds of references. So it's a bit like doing a recursive grep, although it's actually faster than grep because it understands the import graph and can skip a lot of the work. Also, you'll notice that among the results, there are places where it doesn't literally say net.listen. It looks like it's made a mistake here, but in fact, I've created this crafty little example to show you that the tool is able to understand renaming imports and that it's looking for the object net.listen, not just the text net.listen. So it has the precision of a compiler when it answers queries like this. The fourth query related to names needs a little explanation. Often when we're understanding some unfamiliar code, we might have a block of statements and we want to know what are the inputs to this block, to these statements. Another way to think of it is if I was to move these blocks of statements into their own function, what would the parameters of that function have to be? And there's a name for this. It's called the free variables of that block of code. And compilers compute free variables all the time. When you create an anonymous function in Go, the compiler has to figure out which variables need to be allocated in a closure. We're not strictly asking for the free variables. In this example here, we don't want to know about log.fatal, because if we did that refactoring, log.fatal would still be available in the file scope. So we only want to know about local variables that are used within the block, but are not defined within that block. In this case, the only free name of the selection is x. We don't care about error because it's both defined and used within the block. So I'm going to give you a little demonstration now on some code in the FUMPT package. Excuse me one moment. Sorry. So here we are. We have a function. I don't expect you to understand this code, but it's just a block of code. And I may want to answer the question, if I was to extract this block of statements into its own function, what would the parameters be? So I do a free variables query, and it tells me that there are 6 different things that are used in this block. 4 of them are, in fact, different features of the receiver variable p. So it looks like a good way to do this refactoring would be to make a new method and just give it p as a receiver. It also needs 2 further parameters. One is a string, and one is a byte slice. So even if you don't go ahead and do the refactoring, this kind of query can help you understand just what the inputs are to a block of code. So what's going on behind the scenes here? Well, each time I did one of these queries, the editor constructed a Guru command. And Guru is a command line tool, but it has a very simple command line. It has basically just 2 parameters. The first is the mode, and this expresses what kind of query you're doing. And the second is the position, and that tells the tool where in your source file you are. So it could be the position of the current cursor, or if you've done a selection, it would be the beginning and end positions of that selection. And so for the referrers command I just showed you, the command line that my editor constructed is like this one here. And the tool will then open that file, find the offset at byte number 3669, notice that it's an identifier, this time new printer, and then it'll do a referrers query and find all the other occurrences of that name throughout the workspace, and it'll print the results out using a very traditional compiler diagnostic format. And the advantage of this simple command line interface is it makes it very easy to add new queries without having to change the editor in any way. And the output format that it uses is also a very traditional compiler diagnostic format, and nearly every editor already has support for displaying and stepping through the diagnostics produced by a typical compiler. So this slide shows you the set of query modes. There's about a dozen, and we've seen the first 4 already. The remaining ones I'll show you in the rest of the talk. You don't need to read the text here. I just want you to know that there's about a dozen, and it's easy to add more. Because of this narrow bottleneck, this small interface between the editor and the tool, it's very easy to add support for these features to any other editor. The community has contributed about 8 editors worth of support here. And if you have an editor that you use and it's not on this list, please go ahead and add support, and I can do code reviews, and I'll add you to the documentation for the tool. Really, the minimal support you need is the ability to run an external tool like a compiler and to display its diagnostics. Some of the features need a little extra work. I didn't show you, but it's possible to actually type in a buffer, not save the buffer, and then make queries. And the editor can save the modified buffer and pass it to the tool, so it'll use that file in preference to the one that's on the disk. So it even works for unsaved edits. Other features like highlighting and jump to definition need to parse the output of the tool and then take some kind of editor action, like move the cursor or display some highlighting. And so for those, to make it easier for the editor to understand the output, the tool has a -JSON flag, which causes it to emit structured output in JSON notation. So in the image at top right, you can see that when you alight on the fprintf name in the func package, this is the command that the editor would create, just as soon as you stop typing. And the response of the tool, it tells you the enclosing set of syntax nodes. So it would say, you're in a function call, in a return statement, in a function declaration, in a source file. It tells you the package you're in, which is funct. It tells you the identifier on, which is fprintf. And then this last part, same IDs, tells you the set of other identifiers in that same source file that refer to the same thing. And it's this structured information that the editor uses to add the highlighting. So this is enough about how the tool works. I'm just going to show you more features from now on. So the next set of features are related to types. And types are critical for understanding the structure of a program. They tell us the layout of our variables in memory, how much space they take, what operators we can apply to them, what fields they have, what methods they have. The type checker also has to do constant arithmetic, because constants may appear in the types of arrays. And so that information is available to us if we use the type checker. And also, Go has an unusually implicit relationship between concrete types and interfaces. And it sometimes can be hard to know what interfaces are satisfied by a given type, or conversely, which concrete types can be used to satisfy an interface. But the type checker can give us this information. I want to take a very brief digression and talk about some of the historical adaptations that programmers have made because of the lack of type information, the unavailability of type information in their source code. Microsoft C, for many years, used a notation invented by Charles Simonyi, who was the designer of Microsoft Word and Microsoft Excel. And in this notation, you would encode some of the type into the name of the variable. So instead of just saying foo, you would say m_psz foo. And this means this is a member variable, a member of a class C. It's a pointer to a zero-terminated string. So you get this notation, which was jokingly called Hungarian notation, not just because Simonyi was Hungarian, but also because it looks extremely foreign. And even in more modern languages like C# and Java, it's quite common to see that the variable name incorporates part of its type. So observer equals new observer is common to see. Although in Go, we tend to use much shorter names. So I'm going to show you now two of these queries. The first is describe, which lets you describe pretty much any piece of selected syntax, and it'll tell you all it knows about it. And the second is implements, which finds the relationship between concrete types and interface types, or their methods. So we're going to go now to a little web server program. And here we have a function that I hope all of you recognize has the signature of an HTTP handler. If we hover over response writer, which is an interface, and do now a describe query, the tool says that this is a reference to an interface. It tells us its size in memory. It tells us that it's defined with 3 methods, and each of these is a link to the declaration, so you can find the methods quickly. We can go to rec.url. So this is the URL field of an HTTP request, and do a describe query. And it says that this is a reference to a field of a struct. It tells us where it's defined. It tells us all the methods and all the fields. So each of these queries is saving us several trips to the documentation. We can ask about a sub-expression of a larger expression. So this is a function call, or rather a method call of an interface. And describing it says that this is a function call that returns an HTTP header. And it tells us all the methods that are available to us that we might want to call. In this case, we're calling set. This thing here, barmy, is a constant. And if I do a describe here, it says this is a reference to a constant of type Celsius, whose value is 26.6, and 26 2/3. So it's done the constant arithmetic. It was balmy in New York. That's probably cold for you in Denver. And then finally, you can describe a package like log, and it just gives you a summary of the entire API of the package that you can search through and find what functions are available. So let's move now to the implements query. If we go to, let's say this variable w is a response writer, and we now do an implements query, it says this is an interface, that's implemented by 4 different types. They're all pointers to private types inside the HTTP package. Furthermore, it's actually, it itself implements another interface, the IO writer. The Celsius type, if we do an implements query here, it says that this is a basic type. It's a floating point number. And it implements fump.stringer. That's because it has a string method. And if we go down to the bottom here, there's a type called handler. And if I do an implement query on handler, it says that this type implements HTTP handler. That's because it has a serve HTTP method. So the third set of features relates to aliasing. So what is aliasing? Aliasing is the situation you get when you have 2 names for a variable. In this little program here, we have a variable called x. We take its address and put it in the pointer p. Now that variable has 2 names, x and star p. And anytime any of those names appears on the left-hand side of an assignment statement, the effect of that assignment is observed by all those aliases. And this is a completely normal feature of pretty much every programming language since ALGOL. But it does mean that in order to understand a program, you have to really understand the structure of aliasing in that program. And this is not just about pointers. In Go, there are many types of references, as Francesca was just saying. We have slices, which are references to an underlying array. We have maps, which are references to a hash table. We have channels, which are references to a queue with locking. And we have functions, which are potentially a reference to a closure, which is a struct containing variables. So understanding aliasing is critical to understanding programs. And there are analysis techniques that we can use to help understand aliasing. So I'm going to give you now the extremely high-level view of pointer analysis, which is one of those techniques. It's a complex topic. I'm not going to go into too much detail. There's lots of documentation at this package at the top here. And I did a talk on it a couple of years ago that if you want to go deeper. But I just want to give you a flavor of what it does. So it's a whole program analysis that can answer the question, which variables might this pointer point to? And the way it works is it builds a graph. And every node in this graph corresponds to an expression or a value in your program that is a pointer. And then it analyzes all the assignment statements in your program and builds edges between these nodes that represent assignments that copy values or the flow of values through your program. So in this little program, we have 4 pointers. We have p, we have q, which is the parameter to the function, we have r, which is the result of the function, and we have s, which is the result back in the caller. And we also have 3 assignments. We have the argument passing, we have the return statement, and we have the result passing. So this creates the little graph you see here. Then we look at all the places where we take the address of something. So in this program, there's only one place. We take the address of x. And we add a set, annotate a set onto the pointer p, called its points to set. And this set here says that p may point to x. And now you can start to see how we can use this information. It's really a transitive closure problem. By starting with any pointer, we can follow through the graph and find all of the contents of all of those sets. And those are the sets of things that that pointer may point to. There's a lot more detail. I'm not going to go any further, but that's the gist of the analysis. So once we have an analysis that can understand aliasing, we can start to answer a lot of questions that are important to programmers every day. So, for example, most directly, what does this variable point to? What does this pointer point to? For an error variable, we can say what kinds of errors might be actually in this interface value. We can also answer questions about the call graph. This is the relationship between a function call site and the function or functions that it may call. Once we know what every variable points to, we know what potential values of a dynamic function call might be. Or for an interface, when we know what concrete types it might point to, we know what potential methods might be called in a dynamic method call. And we can use this information in reverse. We can say, who might call this function, including from dynamic calls? We can also find out how a function might be called in a path of function calls starting at main. And this is useful when you find yourself in the middle of an unfamiliar code base and you want to know, how on earth did I get here? And we can also use this information to understand the relationships between sends and receives on channels. So in this little program, there's 3 channel operations: M, which makes a channel, S, which sends a value on a channel, and R, which receives a value from a channel. In each case, the name of the channel variable is different. It's CH, CH1, or CH2. But when we use the pointer analysis, it can tell us what these channel references, which channel objects they actually refer to. And in this case, the analysis concludes that CH1 and CH2 both refer exactly to the set containing just M. And because these 2 sets intersect, we know that these send and receive operations may communicate with each other. One last thing before I get to the demos. On this slide, each node represents a package in your workspace. At the bottom, we have errors, which is pretty much the lowest level package. And at the top, we have your application. And in the middle, we have infrastructure packages like HTTP. Let's consider a query starting at the HTTP package. Certain kinds of queries are forwards analysis. That means that they need to conceptually look at all the packages that are forwards of the starting point. So they need to look at all your imports down to the bottom. For example, a query to say, what's the type of this thing, needs to load all of the dependencies. Or where's the location of the declaration of this name? It's a forward query. Some queries are backwards queries. That means that in addition, they need to look at all the packages that are above the query package. For example, when you say, what are all the set of references to this declaration, you need to potentially look through all of the workspace to find the answer. And the implement query is another example. Pointer analysis is conceptually one of these backwards analyses, but it's too expensive to run pointer analysis over all of your workspace, especially when you have dependencies that run into millions of lines. And so we make a compromise. We say that in order to use these pointer analysis features of the tool, you have to give it a little bit more information. And you have to give it what I call the scope. And this is a set of packages that you're interested in. So in this example, the scope is just a single package, my app. But it might be the application you're working on any given day, or a pair of applications like a client and server, or an application plus some tests. And then the pointer analysis will restrict its attention to just the packages that are forwards of those starting points. So the key takeaway from this is that to use the pointer analysis features, you have to give it a little bit of extra information. So now we'll go to the demos. So let's go to the web server again. And we'll look again at this variable w, which is an HTTP response writer. So this is an interface value, and I'm going to do now a points to query. And the analysis thinks for a little, and then it says that this variable w may contain two different concrete types, a pointer to a HTTP2 response writer, or a pointer to an HTTP response. So these are internal types inside the HTTP system. And it actually, because these are both pointers, it knows what they point to. So for example, you can actually find the place where it creates the HTTP response variable that is what my application is using. So it lets you bury down through interfaces to find the real allocations of the objects you care about. Let's try another one. So if we go to the string method here, we can ask, sorry, let's go to the error function. This call to listen and serve returns an error variable, and we can say what errors might be in this variable. So we do a which errors query, and it thinks again, and it comes back and it says that there are three different possible types of thing in this error. One is enval, which is unlikely because it usually is a sign of a bug in your program. And the other two are net.op error and syscall.errorNote. So this tells us that the possible errors from this web server are network failures and system call failures. So that's plausible. So this kind of query can be useful to make sure that if you're trying to consider the possible error cases returned by a function, that you've handled all the ones that are relevant. So now we'll look at some call graph-related queries. So this is a call of an interface method. And we can now ask the pointer analysis, what are the possible callees of this dynamic method call? And it says, this dispatches to two possible implementations of the header function in this application. And we can again jump through to find the declarations. We can ask the query in reverse. We can say, starting at a function, such as the string method of Celsius, what are the callers of this function? And there are no direct calls in this file, but this function is still called. And it's called by a dynamic method call from down in the funct package. And so if we go here, you'll find this is the actual call in the funct package that calls the string methods up in your application. And finally, we can ask the question, how is this function reached in a series of function calls starting at main? And so we do a call stack query. And the analysis comes back, and it gives us a whole stack of calls. And this stack has handle root, our starting point at the top, and then a series of function calls that are inside the HTTP package. And then finally, it pops out at the bottom at main. And so we can walk up through this set of function calls. And you'll notice that one of them is actually creates a new Go routine. That's the Go routine that handles your HTTP requests in separate Go routines. And finally, it pops out at main. So you can use this kind of query to find how is this function actually being called in this program. And finally, I want to show you the channel peers query. So this one lets you ask, what are the operations that are sending or receiving on this channel? So here we have the handleCon function in the chat server. This is the function that handles one client connection. And if we ask who is using this channel here, we do a peers query. Sorry, wrong one. A channel peers query. And it says that there are several places where this channel is being used. It's allocated just up here. It's sent to in 2 places. One up here in the broadcasting Go routine that sends messages out to every client. And once here when it emits the welcome message as the client first joins. And it's received from in this other Go routine that takes the messages for each client and sends them out over the network. And it's also closed in one other location. Now, I don't want you to get hung up on the mechanics of this particular program. The point is that it's a program that uses channels as first-class values. And so sometimes they're called CH, sometimes they're called CLI, sometimes they're entries in a map. They're first-class values in the program. But a pointer analysis can join together these sends and receives and give us useful information. So I'm just going to talk briefly about 2 challenges and some future work I'd like to do. So the first challenge is that the design of the tool is stateless. That means that each query that you saw here read all the source code it needed, did its computation, printed its results, and threw away that information. There's no state saved between invocations. And this is nice because it simplifies the design a lot, and it also eliminates a whole class of bugs. It's taken a lot of work to make it fast enough in this model, but still it's not always fast enough. If you have a workspace with a couple million lines of dependencies in, some of the queries that have to do the reverse queries may take appreciable time. So I think a future improvement would be to use a disk-based cache of type information. And Robert Griesemer has redesigned the notation for type information that the compiler uses. I've worked with him to make sure that it has position information so that the Guru tool can use that same format to save information from one session to the next. I'd also like to use an FS notify-based daemon, so a long-lived process, that listens for changes to your workspace and then reloads immediately the changes so that it always has a cache of what's going on. Implicit in this is that we will be using a cache, in effect. We'll be sacrificing some freshness for better performance. But I think I may have had too much of a kind of compiler writer's mindset of correctness in the design of this tool. And I think really, for an interactive tool, you can tolerate a little bit of incorrectness as long as it's fast and useful. Another thing to say is that the changes I'm proposing here don't change the interface at all. The command line interface is a very narrow bottleneck, and all of this can happen behind the scenes. So the editor integration needn't change at all. The second challenge is pointer analysis. It's clearly the source of some of the most impressive and precise results that the tool is able to give. However, it does require this extra piece of configuration, the scope, the set of packages you're interested in. And it also requires input that completely compiles. And that's not ideal for an interactive tool like this that you might use when you're editing your code. I run the pointer analysis on Google's multi-million line code base every night, and it's actually a better fit for code that's checked into the repository because it always compiles. So I think for the call graph queries, we can use simpler techniques to give less precise results, perhaps with an indication in the output that you can use pointer analysis if you want, but you're getting partial information if you don't want to use it. Another thing is that the analysis can be slow. It's a complex analysis. So what I plan to do is to run it not just for a single query at a time, but to run it for the whole workspace to save the results and then to use a cache of those results so that it's faster. And again, to indicate if you're using a stale information and give you the option to update it. And one very local optimization is just to optimize the set data structure. The point is the key data structure in pointer analysis. And it's already been highly optimized, but I think there's still room for further improvement. So that's really the end of my talk. But this project has actually involved the help of a lot of people. My colleagues at Google who've reviewed the tool, plus all of the libraries beneath it. People in the external Go community who've given me lots of features and ideas and code reviews. And of course, the people who've integrated this with a whole variety of editors. And so if your name is on this slide, I'd like you to stand up so that I can say thank you. Thank you.